I want to present something quite different, computer modeling of particle transport and deposition. And hopefully we'll find areas that we can collaborate more in the future. I'll be talking a little bit about, as I mentioned, about aerosol transport, but from computational point of view, and then do a little bit of discussion of computer modeling approach, and something about indoor and outdoor application, a little bit about respiratory application, and conclude. Basically, in most cases that we are dealing with, the airflow is in turbulent state of motion, and that actually complicates things quite a bit because there is not a fully resolved theory for turbulent flow. There are different ways of simulating turbulent flow. It's a big issue in fluid mechanics. Actually, with the advance of computer, we can actually do basically direct numerical simulation, so-called, meaning no approximation, we can resolve everything, all the small eddies that move in turbulent flow. But this is, is very time-consuming, and it's not really for practical application. You can do it for research and understanding, but not for real application so far. Maybe in future that become possible. The next level is actually the large eddy simulation, that you model or compute the biggest eddies, but model the smaller eddy one, smaller than your grid. And this is now used extensively in weather prediction areas, as well as in many other applications, and is a possible method. It's still extensive and somewhat expensive to do, but it's possible. Then the other class of problem, which is more practical, are so-called RANS model, Reynolds stress average model, and stress transport model and two-equation model are commonly used. And in this way, you average everything, find the mean flow, and then compute how other things happens. One thing that's important is, particles we are of concern to us is very tiny, typically. They are in micron, submicron range, and these are smaller than turbulent eddies. That means even if we do some kind of a RANS model, we still need to find a small fluctuation of turbulence, and those effect is critical to disperse the particle around, deposit them, and things like that. If you're doing a direct numerical simulation, essentially you resolve everything. You don't have to worry about it. If you do, subgrid scale modeling are needed when you do, large eddy simulation. Even those smallest eddies, smaller than the grid, could disperse particles significantly. When a typical application, which we use RANS model, that means average everything, then we use so-called Gaussian filter model, eddy lifetime model. Different approach are possible. And I don't want to show you a lot of equation, but I'll show you one. Here is, in this equation, U bar is the average flow computed in some way by some RANS model. And then, use kind of this model was introduced by Thomson some years ago. And you can simulate, essentially, this zeta here is actually some kind of a white noise excitation. So you can actually, knowing the time scale of turbulence and average flow, you can actually generate the instantaneous velocity with appropriate fluctuation and time scale. And that can be used among other methods to do that. So anyway, we can simulate flow in a variety of approximation these days. Then we have to see how each particle moves, and we're going to start looking at the spherical particle and later on fibers. A small spherical particle in the air is subject to drag force, lift force, because of the shear in the flow. If they are larger than a few micron, gravity is important. If charged, electrostatic forces are important. And if you're in the nanometer range, then the Brownian forces are important. And in fact, you can actually include all of these terms in your simulation and essentially follow track millions of particles as needed. The Brownian motion part actually, of course, is well known, but in implementing in computer model, we did this work some time ago, and now it's commonly used in codes. This is an old paper, actually shows the simulation of Brownian force as a white noise process, which is randomized impact effect of molecules on a particle, sort of. We actually have a course web for this, and there's a Java applet there that you can actually go in and put down your particle size and density and velocity, etc. You can actually simulate Brownian motion in a few seconds if you want to, basically. This sort of validates the Brownian motion. You do computer model, you got to validate every step to make sure it's actually properly done. These are RMS displacement versus time. Again, the solid line is the exact solution for a point source in a constant velocity flow or essentially from point source. And the dashed line is some very simple simulation that we did some time ago to verify the Brownian motion. With all of these, you make a lot of assumption, of course, and you have to validate your model to make sure it predicts with reasonable accuracy what you want. The graph I'm showing here is actually in a duct flow, shows the deposition velocity, which is flux of particle to the wall, per unit time, per unit essentially area, versus particle size. The diameter is shown up here, but the actual parameter is really relaxation time, which is proportional to diameter square and density of particle inversely with viscosity of fluid. Theoretically, the deposition velocity should correlate with tau, but that's the way sort of it varies here. For a small particle, nanometer range, Brownian motion is very important. You get a lot of deposition. As the size increases, the deposition decreases. The little bubble, small circle here is actually experimental data of a large number of people collected in this case by Papavergos and Hidley's paper. And the expectation, of course, was as the size increases, you decrease and decrease the deposition of particles. It turned out when the flow is turbulent, something strange happens, and at certain size range, it actually increases. And increase is quite sharp, and a lot of people verified it. These all the data from very famous people in aerosol science shows that there's a definite increase. And the increase is, this minimum is about 10 to the minus 5, this is non-dimensionalized, to about 0.1. That's 10,000 time increase. So the interaction and the reason, of course, is interaction of particles with turbulent eddies, and that causes this huge increase. Trying to do this properly in a computer model actually takes some effort. And here there are some of the earlier models we have done, some DNS model and so on. Actually, we can capture this trend more or less, which shows that the model actually is probably working reasonably to an extent. Actually, this model was implemented in the Fluent code years ago, and then I was receiving a lot of calls that Fluent calculates wrong answer. I was worried about it. So what we did here a few years ago, we actually tried to run Fluent and run our code and make a comparison. Here is deposition velocity, again, same graph, and the data is green dots here from Papavergos and Hidley. If you use sort of Fluent code on one of the commercial code which has the model in there blindly, this is actually K epsilon model without any detailed correction, and this one is a stress transport model which is anisotropic and so on. I mean, one of issue, of course, is the turbulence is quite anisotropic near the wall, and that's important. And essentially, it seems to miss, by a factor of 1,000 in this range. That for a very big one and very small one, they do okay, but in the intermediate size, they don't do very well. However, if you do the correction needed, basically you can get the right solution. Here, basically, we use the Fluent as the main medium to calculate the velocity, but use our own code to essentially calculate the particle tracking and deposition. And the key component, actually, we found out is very simple. Very close to the wall, the velocity fluctuation of the turbulent flow approaches 0 with y square. And that's basically because of conservation of mass that follows mathematically. And the Fluent, the way it calculates, does a linear interpolation. And if you compare the linear curve with the square term, there's a dramatic difference, and that causes some of the error. So by accounting for that, you can actually get a better answer. A number of people are doing this these days. I mean, Dehbi's group and other people have done this kind of correction similar to this, and the answer become much improved. I think Fluent is also doing to improve it, and we'll see what happens. Okay, this is actually a shoes that's going on the floor, and we look at the suspension of particle from flooring. And actually, we did this experiment at Clarkson, and my colleague, Andrew Fellow, who's my collaborator, we have a number of students walking, and we essentially tag them with sampler and try to make sense of the process of resuspension from flooring to air pollution, basically, which EPA believes that there is a source of additional air pollution indoor. Unfortunately, every student walks this way. Some go maybe very slow like myself, and some go very strong. And each one, the data was so scattered, we couldn't figure out anything. So we made a mechanical shoes here, actually, as you can see, which is essentially simulate foot motion regularly. So the data from this, we could actually try to model and understand the process. Then, after the particle is suspended, you can essentially, the model I described, you can follow the particles, see how they deposit, basically where do they go, how much gets through the, through the ventilation system. If there are people here, how much, is going to affect those people, and so on. And I guess we can go to the next level. Okay. Well, here is a little room with two people, mannequin sitting, and one of them has a cold and coughs. And the question is, what's the chance of the other person catching cold? Or better question is how to design the air conditioning system to try to reduce the, the potential for transmission of disease and things like that, basically. That mannequin I showed you was very crude. We have done actually more work with a more realistic mannequin. This work was supported by EPA and was a collaboration between Syracuse University and Clarkson University. They have done the experiment for this setup, and we have done the numerical simulation, and the details are in some papers which are available. And you can actually follow the trace the particle reasonably well. This is actually a plane. Again, you have a passenger who has cold and coughs, and the germ spreads all over. And the question is how to design the air conditioning system, again, to minimize the spread of germ in flight, if possibly. We are also looking at, outdoor kind of situation. This building here is actually called Center of Excellence Building for Energy and Environment, built in city of Syracuse near two highways. Actually, two interstate pass by. The building is just built actually very recently and is designed to sample air pollution near highways, and it's being instrumented and so on. We have done actually a numerical modeling of this. This is during construction a few years ago. This is a schematic, and this is the final building which is built. We have done testing on this to understand the process of wind flow around the building and the particle transport, and hopefully try to if we could, to basically try to place the sampler in the proper position so that it works properly. This is our wind tunnel here. It's actually an aerosol wind tunnel, and this is actually a high-speed wind tunnel, I think. We have an aerosol wind tunnel about the same size, and this is the basically the model of the building that we tested. And also, we also did computer modeling of that. The computer modeling was done in several different ways, and turned out that LES model actually works probably best. It's very time-consuming, but it works best. Unfortunately, this video is not working, so I'll probably skip that. We did experimental work in the tunnel and did computer model and tried to compare them to make sure the model is working. And these are some of the, comparison done here. This is PIV measurement at a section of the building, which is done in the wind tunnel, and particle image velocimetry. You can measure the velocity field non-intrusively and shows a kind of a reattachment zone in this area, basically. And then we did RSTM, which is a sort of an advanced turbulence model used in industry quite a bit. And no matter what we did, we could never get this reattachment correctly. So RSTM, essentially for a complex geometry, seems to have problem. But LES seems to, large Eddy simulation seems to capture this, more correctly, but it's far more extensive. You need a lot of computer time and effort to get it to work. We have done a lot of this comparison, and these are again available in publication. This is another section of the building. Again, PIV measurement here, RSTM here, and LES here. Again, comparatively, LES does better. RSTM in this case captures the general feature, but misses some of the detail. There's another simulation in a street canyon. You have some emission from a flooring, and and again the flow transports the particle, and you get deposition at different location. We have done a comparison for the same kind of geometry. This is actually geometry of studied by Moroni and co-worker. They did a wind tunnel testing for a CO2 emission and measured the concentration. Their data are shown in here, and our computer model also shows there are some differences, obviously, but general features seems to be captured. Another interesting study I thought I'll mention here, this is Peace Bridge between Canada and US. This side is Buffalo, and this side is Canada. Peace Bridge is a very busy bridge. A lot of trucks come every day from Canada or vice versa, and carry food and other things. And there's a custom plaza here, actually, and the truck has to wait here to clear custom. And you can see the residential area is just next to that area. And that is a source of some issues. In fact, Dr. Lubaga Mukasa, he's a physician at University of Buffalo, a specialist in essentially lung disease. And he wrote a paper a few years back when people went to him for asthma and other issues. Essentially, he kept track of their record. And in his paper, he discusses that each point here is actually a person with asthma in this region. The Peace Bridge is right here. This is the connection that goes to Canada right from here. And this, you can just cursory look at this graph, shows the concentration of people with asthma is very significant close to the Peace Bridge and decreases as you go further away. In fact, he reports that this area has 7 times more people with asthma compared to the national average. In fact, when he showed me this picture, the impression was probably Peace Bridge has to do something with it. The pollution from the trucks and so on may be causing the asthma. And we studied this work also, and this is the schematic of the region. This is the bridge coming in. This is the custom area, and this is the residential area. This is a little bit more detail of the flow simulation. And this is a little bit of, shows the emission from the bridge. And you can see that near this area and custom area, you have higher concentration. Red means more pollution and basically goes to lighter weight. So the area that we get peak concentration coincides with the area that we basically have higher concentration of people with asthma. My colleagues, Peter Jake and Andrea Ferro, was a collaborator in this work. We have actually a mobile truck with MIPS on it and so on. They spent the summer in 2002, 2003 in Buffalo and made measurement of the actual concentration of particle at different locations in the city. This is actually, again, the Peace Bridge is right here, and they made measurement very close to the bridge and different location. Again, we used their data for the emission from bridge and try to compute the concentration. It seems that the trends are more or less captured with the data that they had. And this is probably, was in some respect kind of lucky because the results are too close. I think, typically you have at least 20–25% error, but we also looked at, a project for NIOSH. We looked at inhalation of particle and fibers, mostly fibers actually. We use there are various models for the lung available. We use so-called a multi-level lung because lung has 23 bifurcation. People have gone up to about 6 or 7. We have done 3 or 4 ourselves. But it's hard to do the entire lung in details. Of course, there are approximate models and so on that this morning was discussed and so on. So essentially, we do each piece, and then we calculate all the properties. It shows different branches. At the intersection, we calculate all the properties, including all the velocities, turbulent intensity, etc., and feed it to the next level. And basically, we can continue this, and the hope is, it's not done yet, is after several bifurcation, hopefully it repeats itself, and we can sort of estimate the property after that. We have gone to 3 or 4 bifurcations so far. We have done spherical particles. We had this glitch that this one probably doesn't work. Let's go to the next one. The NIOSH project has to do with fiber, mainly of the problem with, of course, asbestos and elongated particle. Elongated particles are much more complex to model because not only they have translating, they're rotating, and they're affected by the rotational motion and so on. So you have to essentially solve this coupled equation. And also the Brownian motion could be important, especially if you go to something like nanocarbon tube and so on, which are small, that could cause other issues, basically. We have been working in the area of fiber motion, actually from some time ago through some project with IBM and Xerox. And these are, again, deposition velocity versus, for dots versus relaxation time. And there's not only a single graph. There are a bunch of them depending on the aspect ratio and other properties. And the model seems to predict at least the feature of experimental work, which are by Shapiro and Goldenberg in here, and actually our own experimental work at Clarkson. And the fibers, essentially, this is a graph that shows from the side view, the fiber is moving axially and, of course, rotating and translating and depositing. And that shows, this was actually a direct numerical simulation done some years ago. We got a little ambitious, actually, and did here more complex fibers, actually, not just the straight fibers. So you can do some of that. This is actually for the lung. I hope it works. Let's see, OK. So the fiber is coming from the middle of the, of the lung, essentially, and it translates, and it goes through the, essentially, the passage. This, of course, the fiber is exaggerated in size significantly here so that we can visualize. This one, let's see. OK, this is near the wall, and you can see in the wall there's a strong shear, and the fiber stays essentially parallel to the wall with a small, and then some rotation near the end that before they leave. The deposition of fiber as part of this NIOS project was done basically, in this project. We had, Dr. Chang from Loveless Institute and Clarkson jointly working on this. They have done the experimental data, and the experimental for fiber deposition versus relaxation time is scattered dramatically, as you can see. The problem is tau, which is the relaxation time, does not fully characterize the fiber because the aspect ratio is important and need to be accounted for and so on. But basically, we did similar simulation to the range of data that they had, and they are at least the same order. Still, probably there are questions to be answered that what are the specifics, but the order seems to be the same. We also did quite a bit of work on nose, the trans is part of this project also. We had both lung and nose. And nose, of course, is quite complex. And here is some particle entering into nostril and going through different parts and depositing. These are a spherical particle here. We have done fiber also. This is a stereolithography image of the nose, which was used in the experimental part of the, of the study, and we could essentially, feed particle from here and then essentially dismantle it and measure on each part how much particle are deposited. These are for ultrafine computer model comparison with mostly the work of actually Chang et al. And Swift et al. And so on. These are nano range, very small, diameter, and at 4 liters. These are ultrafine particles, actually. These are not fiber. These are small particles, basically. And you can see that, for a small particle, we get a lot of deposition. As you go to larger, they decrease. And of course, to the bigger size, they're going to increase again. And these are done for 2 different breathing rates in here. And the comparison is reasonable with some deficiencies in certain size range. But if you plot all of these versus Peckley number, actually the data more or less collapses to one graph, showing that the diffusion is dominant process for this nanoparticle. We have done the same study for larger size particle, and this is done by others as well. This is again a deposition percentage versus diameter for different breathing rate. Again, if you plot them versus relaxation time, they collapse. This for larger size, impaction is dominant. Either impaction factor or relaxation time correlates those quite well. These are some comparison of our fiber study in the nose. Compared with the data of Kelly and other people, and with the spherical particle and some experiment by Su and Chang and others. Actually, interesting thing is, this is of course versus impaction parameter. And if you look at the detail, the fibers data is in the lower part of this graph, because the fibers typically stay straight in shear field, and and that will reduce the deposition, at least in the nose. It seems that way. We have done more complex geometries. This is actually the nose and and the laryngeal cavity and trachea and the bronchus. Unfortunately, I found out this movie doesn't work here, so that's okay. Well, just to conclude, computational modeling certainly, helps to provide some insight into particle transport deposition in various applications, hopefully. And it could be a tool for testing various scenarios that virtually, essentially. We are doing some work on trying to do, operation essentially virtually on the nose or other part of the respiratory tract numerically to make sure that, the patient gets the right treatment. And I think the future has some promises in that arena. I want to thank my colleagues and ex-students around the globe, essentially. They all helped in different pieces. I gave you a sort of overview of what is going on here. And this, actually, I'm going to stop here and thank you, answer question. This is a direct numerical simulation of two-phase dense flow that the particle collide and move. So it's much more complicated, and but it's more interesting to look into and how it falls. Thank you very much.